So you can think of it as an extension of whatever we have studied on overlays so far. Okay. So before I start actually discussing the paper, today we look at a very interesting paper. It's about an architecture called Catapult. This was built primarily in Microsoft Research. This is a 2014 paper, so it is one of the earliest large-scale practical commercial applications of an FPGA accelerator. And what is nice about this paper is they've described not only the how they build the accelerator and how they measure, but also a lot of the other practical considerations that they had to take care of in order to do this, build this on scale in a data center. So it's, it gives you a very nice rounded perspective of all the things that you have to think about. So before we proceed, right, to actually look at the paper, let's just, do a quick recap of why overlays are necessary, what are the advantages of overlays, what are the disadvantages of overlays. So somebody wants to maybe volunteer why are overlays required, or when would you like to use an overlay?
When we want to reuse an existing, I think multiple times we use it.
Okay, that's a good point. So you have a computation and you want to use it multiple times. Now, when you say multiple times, in what context do you mean multiple times?
Means like in like replicating it multiple times on the same.
I could just build a kernel and replicate it, right? I could have an IP, for example, and replicate it. Would that not achieve the purpose? What is the difference between that and an overlay?
The thing is, we save time, which we have already implemented version of it.
Okay, not quite. So I see that, yeah, there are a couple of comments in the chat. So the difference between an overlay and just a regular accelerator. See, any piece of IP that I build on the FPGA can be replicated. Right? If you think, for example, of I can build as let us say a floating point unit on an FPGA, right? And then I can keep replicating it, right, many times to achieve parallelism. So the key here is that what an overlay allows you to do is to program at a higher level. So if you have something that an application that needs to be programmed or configurable or whatever, there are two ways to do it. One is to have a parameterizable IP that you then, a parameterizable RTL block or a HLS block or something that you then instantiate, right? But what an overlay allows you to build is, if you have a more complex function that has to be programmed at a higher level, right? An overlay gives you an easy way to do that by taking care of the underlying implementation. Right? So that is one point. Yeah, so somebody, Tanmay, has said faster compilation time. So Tanmay, do you want to elaborate?
As the most of the design is pre-compiled by the generator of overlay, we don't have to we don't require high compilation time to use that hardware piece.
Right. So you don't have to worry about the nitty-gritty details of the implementation. How do I place and route it? How do I close on timing? Which you would have to do if you had a parameterizable block. Right. And the other advantage is, if you wanted to insert something into an existing software framework for acceleration, typically you will end up needing an overlay just so you can interface easily with the software framework. Then you can run a small runtime layer, or in some cases, if you have something that mimics a processor, right? A processor overlay, you can run a small operating system on it, so on. Okay, so no, I'm not sharing my screen yet. So I will share when we get to the paper. Okay, so that is one advantage of overlay. Right. Now, what are some of the challenges that you would face when you are building an overlay? Any thoughts?
First of all, I think someone also needs to build the overlay first of all in order for others to use it. So that is again a painful job initially. And also overlays may end up using more power than our custom made kernel if if we are not using it to its full potential.
Correct. Why would they use more power and potentially more area than a custom kernel?
I mean, for a custom made kernel, we can optimally place and route according to our application. But since the hardware is pre-built, it is some kind of like CPU like kind of thing basically. So instructions are instructions even if instructions are simple, still they need to follow a particular pattern. So they may end up using more resources, I feel.
Right. So this is a common thread that you'll see through this course, right? So anything that requires more programmability becomes more convenient to use, more convenient to integrate, but invariably it will end up using more power and more area. Right? So, okay. So now let us look at this paper. Okay. So,
ma'am, can we also get the issue of timing synchronization with overlay? Like since it's acting first, so we'll have to synchronize our host with the overlay, something like that.
I didn't understand your question. Can you just repeat it?
Do we also get timing synchronization issues with the overlay? It's working at a speed that we have to match our accelerator or host that is running with it.
Yeah, that of course it's not, it is more what I would say is an integration issue, right? So if you want your application to run at a certain speed, now when you design the overlay, you will have to design the system, right? Which means when you design the system, what does it mean? So if there is data which is moving from the host to your kernel, which in this case is an overlay, you will have to take care of, managing the buffer requirements, right? Matching the speed of the computation, right? All those things, yes, definitely you will have to take care of. But, and so it is important when you're actually building an overlay to think also about the system level specs. How will this actually be used in a system? And, if you are putting that overlay on a single FPGA, you need to keep space to store data if you need to store, right? You need to understand the system level requirements also when, building something. Did that answer your question, Diksha?
Yes, ma'am.
It's a good point. It's a good point. So, so I'm going to basically go through this by, we'll largely look at some of the figures in this paper and talk through it. Okay. So what's very interesting about this paper is it's called Project Catapult, and what I have picked up here is the very first paper, which was published at ISCA in 2014. Okay. Before this, there was, quite a lot of work on, how you would communicate with an FPGA card. As I told you last time, some of the oldest overlays that we have been processor overlays. Right? This is the, one of the earliest papers where they've actually looked at taking an application which is, which could benefit from acceleration. And they have looked at how to design that accelerator, including, some parts of it are an overlay, some parts of it are not. how they would design it, how they would deploy it, how they, take care of a whole lot of system level requirements and so on. Okay, so before we get into this paper, one more thing which is important to understand is that today you'll hear of two kinds of terminologies when you talk of applications and acceleration. You'll hear this notion of cloud and edge, right? And we talked about it, I think, in one of the earlier classes. So I hope everyone is clear on the difference between the cloud and the edge. So when we talk about edge, it is typically, a single FPGA, which is, connected to a local server, or, at the most may, communicate over, from that server to a, smaller data center, right? So typically the edge application is something which is, it's a single card with an FPGA and a small host server, typically an embedded server. When you talk about the cloud, that is more of a data center type of, and again cloud, there are there is a whole spectrum of sizes and configuration and so on. So typically when you talk about cloud, you talk about a large scale setup where you have a large number of machine servers, where you have varying workloads, right? So something like the AWS that you're using is what one would consider a cloud deployment. Whereas if you were running a small application to accelerate, let's say a surveillance camera at your gate, right? That would be more of an edge application. Okay, so this paper actually looks at accelerating a specific data center workload related to search in Bing, which is Microsoft's search engine. Okay, and what they have done. So what is new here in this is that at the time that this paper came out in 2014, FPGAs had not been very widely deployed in data center applications, right? And what they have, one of the challenges there, and you will also see this when you look at reconfiguration, is that reconfiguring FPGAs, it takes time, right? So you need to basically design an entire fabric that gets over some of these practical limitations of using FPGAs for acceleration. And we went over some of them in the class, right? What are some of the practical limitations of using FPGAs? One is that you need to fit your function in whatever area is available based on the cost you have to build your system, right? And if you want to run it in a virtual, as a virtual machine, which becomes a very important tool in a data center. Right? If you have used data center CPU servers, most of them work by virtualization. But virtualizing means reconfiguring at runtime, which is slow. Right? And then FPGAs, they do consume more power than a custom chip, right? But at the same time, it allows you to, easily handle multiple workloads, right? So the key thing here is, how are they building? So what they have built in this paper is, it is a framework consisting of multiple FPGAs, right? Connected to hosts, and connected to each other, and this fabric is what they call Catapult. And the accelerator that they have built is to accelerate their ranking service. Okay, so wherever they talk about the accelerator here, they actually refer to this group of 8 FPGAs. Okay, and so here, if you see, right, this is what the board of a single FPGA looks like. Okay, so the board has an FPGA, it has an 8 gigabit DRAM with error control code, and we'll go back, once we go over the acceleration, we'll go back and look at the entire server setup, and why there is the need to ensure that they have ECC in this, and why that provides a stable system. Okay. And then you have JTAG, which is used to configure the FPGA, Flash, which is used to save the different potential configurations, bitstream configurations of the FPGA. Okay, and then this shows a picture of the board which is actually manufactured, and then this is the server that actually hosts the board. Okay, and what is interesting here is that they have a pod. So they have these pods with 48 servers in them. Each server has an accelerator card attached. Okay, and the accelerator card basically this pod they're wired in the form of a torus. A torus is like a donut, so you have wiring on the outside as well as on the inside. Okay? So that's what you see. So, and here they talk about why they had this kind of framework. Right? So can you think of a couple of ways in which designing an accelerator for a data center would be very, very different from designing for the edge? What is different when you think about, for example, the way you use AWS versus the way you have used a simple card which is attached to your laptop? It could be a microcontroller, could be an FPGA, anything. Anyone? So there are two main things to think about. One is that you should be able to easily scale your data center based on your requirements. Okay, so if I have a group of, let's say I have a pod with thousands, I have a data center with 1,000 servers, and then 2 years down the line, so I've already made a significant investment, right? 2 years down the line, let us say I want to expand that data center by maybe adding 50% more capacity or 25% more capacity. Why? Because I get so much traffic. Right? I should be able to easily expand it without having to redesign my entire data center, just by adding extra racks or shelves or something. Right? So that entire data center has to be designed in that way. The second factor with any data center is reliability. Because these systems run for a long time, right? They have to be cooled efficiently, right? And problems do occur. So a server may go down. A card may have a problem, right? You could have, you could even have single event upsets in some of these scenarios, which is actually one thing they talk about even in this paper. Right? And so reliability becomes very important. So for reliability, you need to ensure that you also have redundancy. When you service something in a data center, right? Let's say a server is down or a card is down and I have to replace it. You can't tell a user who's running an application that they have to wait until you shut down the data center, restart everything and rerun. Right? So you have to be able to service the data center by rerouting your applications to other nodes that run while you service whichever node needs to be serviced. So you cannot, it's very rare that you can bring the entire data center down. Right? So you need to make sure that you have both a very reliable operation, and secondly, you have enough redundancy so that you can take care of maintenance and any other downtimes. Okay. So for this reason, so they talked about, why they have looked at these, different types of configurations. So one of the configurations they looked at is you put, multiple FPGAs onto a data card, onto a daughter card, and then you put that card such that a subset of servers access it. Right? So here they talk about the problems with this. So it's very interesting to look at how they came up with this design, actually. So one of the problems with this is that it is not an elastic configuration. So you're limiting your card to 6 FPGAs. Right? So if you need more, then it's hard to map. Right? If you need less, then you're wasting capacity. Right? And then you have to also have design the board in such a way that it is easy to accommodate in a traditional server rack. Otherwise, what happens, the person who's running the data center has to, they have to basically redo their entire, data center design, including, the racks, the network, the power distribution, the cooling, everything. Right? And then finally, they talk about reliability. So the large board is a single point of failure. And so if, that board fails, then because that single board is connected to, let's say, 6 servers, right? I have 6 FPGAs connected to a subset of servers. Let's say there are 6 servers. Then, if the card fails, then I will have to take down that entire set of servers. Okay. So they took this alternative approach of basically, having a small daughter card in each server. Right? And then these cards are connected together with a secondary network. And what they ensure is that they have low latency and high bandwidth on that inter-FPGA network, so that you can actually take applications which are too big to map on a single FPGA and map it onto a group of FPGAs. Right? So this allows you to do 2 things. One is you keep the cost down because you can actually, put a medium-sized FPGA on the server. You don't have to take the biggest one, right? And at the same time, it allows you to, map bigger applications or map smaller applications. So this gives what they call elasticity. Right? And so, some of the factors that you have to look at commercially is, you have to trade off basically what is the performance improvement that you expect with this acceleration versus the fact that, you will increase your total cost of ownership, or what they call TCO, which means, why would the total cost of ownership increase? Anyone? Anybody? Let's say I had an existing data center and I wanted to add, an accelerator card like this, right, to each server. Why would my costs increase? So one very simple reason is because you have to buy more equipment, right? You have to buy the cards that cost something, right? What else? So those are capital costs, right? I need to buy additional hardware. That is a capital cost. How about operating cost? What will change in the way I operate my data center if I add more hardware? Anybody? Yeah, Aditya?
The network requirements, like you might need to re-provision the servers when you're adding additional hardware, or
yeah, that could be one. That could be one. You may need additional networking equipment if you have additional hardware, right? But in terms of operation,
additional space is required, internet bandwidth is required more, also power usage will be more.
Power, yeah, power is a very big thing. So the minute you add new hardware, you need extra power, right? And then the minute you consume more power, what does it mean? You have to cool your data center, right? What happens to any electronics when the temperature goes up? If you've done any basic semiconductor physics class, right? What happens? As power goes up, what happens to the performance of a chip as the temperature goes up?
It reduces.
It slows down. Right? It slows down. Right? Any transistor slows down at higher temperatures. Right? And so you need to cool. Right? Now, to cool often in our data centers, you need space. Right? So all these become constraints. How do you cool? To have airflow to ensure cooling, you need enough space. Right? And so, all this adds to the operating cost. Right? And so typically when somebody is commercially building an accelerator, they will look at, what can they afford? Right? So if you see in this, they actually said, they had set themselves a limit saying we cannot increase our total cost of ownership by more than 30%. And that 30% includes a limit of 10% for total server power.
Ma'am, I have a question here. So when you have a data center with like enterprise class servers present in it, so the network or whatever the cooling facility, everything, it will already be there, and the FPGA cards that you are adding to the server, when compared to the server power, it will take very less power, right? So will the existing power requirements won't be sufficient for them as well?
It depends on what you're accelerating, right? See, you may be taking less power, but you may be running something at a much higher performance also.
Okay. But at the same time, the CPUs won't be overloaded with that, right?
Correct.
Yeah.
Correct. That is why, they are saying the total server power may not increase by more than this, right? But every piece of hardware that you run, so there are two components to power, right? One is the static part of it, and the other is the dynamic part of it. Right? So dynamic depends on your workload, yes. But every hardware that you add will add some static power, because the fact that the chip is there and it is powered on, that inherently burns a certain amount of power. Right?
Okay.
Makes sense? Did that answer your question?
Yeah.
Yeah. So you are right in the sense that, by accelerating some things, your server actually becomes less loaded, right? And you are transferring some of that load to your accelerator. But the accelerator now, the trade-off between how much power it consumes also depends on the speed at which you're accelerating something. Right? So there is a trade-off there which could be application dependent. In addition, you will consume static power in any case. Okay. Right. So yeah. So having looked at this, so I'm going to go through this paper in a slightly different way. Okay. So what I would like to go through first is actually let us understand the FPGA architecture itself. Right? What have they done on the FPGA? How have they built the shell? What is the overlay? And then we will come back to section 2 of this paper in more detail. And then there you will see some of the other, system level design considerations that have been taken. Okay. Fine. So here, basically, what they have looked at, right, is. So let us look at this. Okay. So basically, here there are two goals that you want to satisfy for your for each FPGA, right? So they need the FPGA to communicate with the host, right? They need the FPGA to communicate with the memory on the card, right? And they need the FPGA to communicate with other FPGAs. And then this is required for configuring the FPGA, the JTAG and the flash. Right? And then you have some sensors and they have an SEU unit. So we'll come back to that in a little bit. Okay. So if you remember when we talked about accelerators and overlays in my last lecture, we talked about this concept of a shell and a kernel. Right? And you can see that this architecture also follows the same philosophy. So you have a shell which consists of DDR controllers. They communicate with the DDR. There is a PCIe core to communicate with the host. There is a DMA engine to do direct memory access from the DDR if need be without going through the host. Right? There is an inter-FPGA router. Now this is somewhat special to this kind of accelerator because they have an architecture in which the different FPGAs actually communicate with each other. Right? And you will see a similar thing actually in AWS. So AWS, I think, has 8 FPGAs which communicate with each other, if I remember right. Right? So you need to have some kind of chip that takes care of that that traffic, right? And this has to be low latency and high bandwidth, as they mentioned. Right? So from this, now in addition, right, you need to be able to support a few things. Right? So you have to design your whole accelerator keeping the system in mind. Right? So let us see what are the parameters that they've taken to keep the system in mind. So the first thing is you have to think about your software and how your software actually is going to run. So in their case, their software actually is multi-threaded. So they want to ensure 2 things. Okay, so that the communication between the CPU and the FPGA must have low latency. And this is a very concrete constraint that they have come up with. This must have come up from their system performance. The paper doesn't, one thing the paper doesn't talk about in detail is, why did they decide to accelerate this specific part of the application? Right? How did they get this constraint? What was the system level constraint that comes out to something like 10 microseconds for these transfers? But you can think about how you would get it from a system level application. Right? You can basically say my entire software stack has to run at this speed. This is the bottleneck, right? And for the bottleneck to be accelerated, I need to supply data with this latency. Right? And then this interface needs to be safe for multi-threading. Okay, so basically they get this low latency by completely avoiding system calls and by doing a lot of static allocation. And then they get thread safety by taking a buffer. And so the buffer is basically divided into 64 slots. So you can support 64 threads. Each thread gets a static assignment to a slot. And in the study that they've used in the paper, each slot has a 64 KB amount. Right? And then there is some handshaking for the slot. So each slot has a status bit, tells you whether it's full, right? And then sets the bit. Right? And then the FPGA itself will monitor that bit and then select the slot so that you can basically do the DMA, right? And then transfer it to a staging buffer which sits on the FPGA. Okay, so all this is taken care of in the shell. Right? The input-output handshake. Is this clear at a high level? Any questions here? The second thing that they take care of, so far we talked about this, right? This is the API for interfacing software with the FPGA. So the PCI core connects with the host, the DMA engine takes care of the data transfer in a low latency, multi-threaded supporting way. Then the second thing is you want to have interfaces between the FPGA application logic and board level functions. So, that is taken care of by some of this. This takes care of the configuration of the FPGA, right? And then this is the application which actually runs, right? So that application has to have, it has to have some buffer to, take care of feeding anything that comes in from the memory. Right? It may need a set of status registers to take care of any handshaking between other FPGAs. Right? Right? So all those things will be incorporated into these parts of the shell, which are independent of the application. And typically when you provide a shell like that, you need to have some kind of fixed interface that your applications should follow so that they can make use of the shell. And then, you know, you need to support any kind of resilience or debugging. So what happens if your application fails? How do you figure out what's not working on hardware? Right? And if you used a single FPGA, you could, you know, use something like signal tap for quarters or chip scope for Xilinx, and actually probe signals on the chip as its application is running. But here, you know, they actually need something a little more complex, because the application is running in a data center where it's not easy for you to go and actually look at the board and, you know, see what's happening by looking at some LEDs or, you know, reading some bits there and so on. Okay. So, so the shell architecture, basically, yeah, they say it is about 23% of each FPGA. And if you look at all these, right, they have, so they have 2 DRAM controllers. And here, this is to Diksha's point that, you know, you can see that the, you know, this is the speed at which the memory runs, right? The DIMMs run at 667 megahertz, or if they are using just one, it can run at 800 megahertz. And then you have 4 high-speed serial links, right, which run this. This is probably a Microsoft-specific protocol. I'm not very sure. And this supports, you know, basically FIFO semantics, some kind of floor control, error control coding. And then you have, this must be having some kind of traffic manager as well, the shell. And then they have a single event upset logic, which is to take care of error control. Now the router itself is a standard crossbar. It connects 4 FPGAs together, the PCIe controller and the application. Okay. And then what they have is, how do you decide how to route? They actually have a software stack on top. So they have a software controlled routing table that supports different routing policies. So these can be configured. Okay. So we'll come back to the error controlling later. Okay. Let us now look at how they actually, you know, configure this FPGA. Okay. So they have a service called a mapping manager, which is in software. And what this does is, you know, if you have an application, remember they have a set of 6 FPGAs, right? And so the mapping manager basically can take the entire application and it partitions it into different FPGAs, puts the correct bit stream in and starts it up. Okay. So that is one service. The second service is what they call a health monitor, which polls for failures, and you can use that for debugging. Okay. So we'll come back to this a little bit later. Okay, failure recovery, and let us actually look at the application case study, which is the interesting part. So far we have looked at the shell. Right? Now what we are going to look at is what actually sits here in the application. The remaining 77% of the FPGA, what is it actually used for? Okay. So the application here that they are looking at in this paper is ranking of search. Okay. And they have done all their design in Verilog. It has been a hand design and a hand partitioning. So they basically have an 8-engine Taurus, and they keep one as a redundant FPGA. Okay, so let us just quickly go through the application. So what they have is, this is being used in web search, right? So Bing has a number of you get search queries, right? So as the search query comes, first, there is a cache and it checks if you get a hit in the cache. Right? So if you don't get a hit and you get a miss, they have an aggregator which coordinates, it takes this query, right? Does a search, right? And then comes back and aggregates, right? So this this query is sent to a large number of machines, and each machine has the job of finding a document that matches or a web page that matches, and then you prioritize and figure out which one has the highest score, and then get it back so you can display the results of the search. Okay, so now the part that they are accelerating is actually the ranking service for each document. Okay, so the accelerator here is, what it does is it takes a document, right, and some metadata. It computes some features based on the query, right? Then it runs these, it takes these features and then computes what they call a free-form expression. Is really, you can think of it as a meta feature or a higher level feature. It is some computational operation on these base features. Then that is sent to some kind of machine learning model which generates a score. Okay, and then the score comes back to this aggregator, and the aggregator coordinates all the queries on these different documents and then ranks them and sends them out. Right? Returns the results. Okay, so in this entire model, what they have said is they have done most of the feature computations. All this, which is computationally expensive, has been accelerated. So as I mentioned earlier, what would have been nice is to understand, from a software point of view, how much of a bottleneck this was and so on. We can kind of infer some of it from the results. Okay. Clear so far? If you have any doubts on what the application is and what is being accelerated, this is a good time to speak out, because otherwise you won't follow the rest of the discussion. Okay, so right. So now this application, right, has a pipeline with 3 stages. Okay, to process. All right. So the software basically takes a document, right, and a query, right, compresses the document, and it sends these 3 sections as a request to the fabric. Okay, so that this document has a header with a request. Right? It has a set of features which are computed in software, right? And it has a hit vector which tells you, to what extent does the query actually match. Okay, and the header, consists of a number of fields, right? Now, some of these are, software computed, right? And the rest will be computed on hardware and maybe filled in and sent back. Okay, so now the pipeline basically is this. They have this thing called a macro pipeline. Okay, and the way they allocate the functions are, so this entire pipeline is allocated to 7 FPGAs. Okay, so see, we saw here that there are 3 things that they need to do. Right? The first is you need to basically compute features. Right? Then you need to compute these synthetic free-form expressions, and then you need to run it through a machine learning model and generate a score. Right? So these 3 are the basic building blocks of your pipeline. Okay? And so the way it is architected is they have 1 FPGA for feature extraction. Okay, 2 to compute these free-form expressions. Okay. So this first FPGA is a queue. It manages some of the jobs and allocation of, I'm guessing, the pipeline. Right? Some buffering management and all must be happening here. And this one computes the feature, it extracts the features. Right? Then you have these 2 FPGAs which do the FFE computation, that free-form expression, which is basically some arithmetical combination of these features, all floating point combinations of these features. And they have an overlay which actually does this computation. Okay? Then they take the results of this, compress it, okay? And then they have 3 FPGAs which are dedicated to do the scoring. Okay, and then this is the final score is sent back. Okay. So the 8th FPGA is a spare. So this is used for redundancy. So in case an FPGA comes down, you don't have to take this entire thing down, stop this entire node. You can basically program the spare FPGA while you take down one and replace it or maintain it or whatever. Okay. So this part, so this queue manager basically it tells you what model has to be used. It depends on the language of the query and so on. Right? And so what this queue manager does is there is a pipeline there is a queue from the memory which has all the queries, right? And so the queue manager takes the document and sends it to the pipeline, and then it knows when the queue is empty, it goes to the next queue. Right? And sometimes the next queue may have a different model, so the queue manager takes care of that reconfiguration. And this model reload, of course, is an expensive operation because you need to reconfigure some part of your pipeline. So now let us look at the feature extraction. So the feature extraction engine basically calculates scores for a variety of features depending on the query and document combination. Okay, so this is actually a pipeline of finite state machines. So if you see, they have the number somewhere. So it's this array of finite state machines and 43 unique finite state machines. Okay. And basically, so you take the document, you do some pre-processing, right? And then send this input data in parallel to each of these feature extractors. Okay. So all these feature extractors work on the same data, but they do a different computation. Right? So you learned about SIMD in the last class. This is the opposite in a way. It's a different form of computation. It is multiple instruction running on single data. Right? SIMD is single instruction running on multiple data. So then this feature extraction, these finite state machines, they gather the features and then they send it out. Right? And then basically they figure out, they have some optimizations here. Right? So some features have very similar computations. So they use a single state machine to calculate different features. Right? And this whole so one of the challenges for implementing something like this is that you have the same data going to a large number of compute engines, right? And that can actually create a lot of congestion when you want to route the design, especially because each of those FSMs has to work at a high clock rate to process the data in parallel, right? And so, that is why these blocks are actually organized like this. If you see, they're organized in this, hierarchical way, and the input data is actually replicated. This makes it easier to implement this on the FPGA. And then finally, you have this network which takes all the results, gives a single output stream and takes care of it. And if you see, they have used double buffering here. So the inputs to the feature extractor are double buffered, and that is to increase throughput, as they have learned earlier in this course. Okay. Now we come to the actual overlay which is used here, and the overlay is used for calculating free-form expressions. Okay, so they talk in this paper about another option for them, which is to just take an off-the-shelf soft processor core. So, NEOS is a processor core that's available with Intel FPGAs. Microblaze is a processor core which is available with Xilinx FPGAs. And this is, it's a CPU overlay. Right? So the reason why they have chosen not to go with that is because those cores are single threaded. And we saw earlier that they require massive multi-threading for the kind of computations that they want to do. Right? And this requirement for multi-threading comes from their software stack as well. So instead of using a single threaded processor and tiling, right, because you would not be able to achieve the kind of performance that you want, they have actually developed a custom multi-core processor. Right? And the result here is, that's shown here in this figure 7. Right? So it's a very area efficient multi-core processor, and it is optimized to do floating point operations. Right? So if you see, each core supports 4 simultaneous threads, right? And they have an arbiter that takes the arbitration for functional units. Okay, so that if one thread is stalled on a long operation, other threads can make progress. This is all fairly common kind of arbitration that you would have in any CPU design. Right? And then all functional units are fully pipelined. Right? So the other very interesting thing that you'll see in this entire paper, common thread, is they've tended to use static scheduling instead of any kind of dynamic scheduling. And the reason is it makes your latency very, very predictable. Okay. Right? The third optimization that they've done is to take long latency applications and actually split them into multiple instructions, so that you reduce the length of the longest computation in your pipeline, and that further allows you to improve your throughput. Okay. So because of this, they are they have so the other factor here that they have to consider is because many of these operations are floating point operations. Floating point, as I mentioned, I think to some of the groups that I talked to, is expensive on an FPGA. It takes a large amount of area. So because of that, they typically have, they have this kind of architecture where you have multiple cores actually sharing a functional unit that does floating point computation. And then you need an arbiter to figure out which core actually is using the FPU unit at that point in time. Right? Okay. So all these, so now you have an overlay, and this overlay has its own compiler, as we talked about. That's very common when you have an overlay. Right? And so all these complex floating point operations are basically, they go through a compiler which decides how to subdivide them into smaller instructions, so that you can actually share computation. Okay? And then here again, you see double buffering use. So there is a, the block has a storage tile which is double buffered. So that allows you to load your document in parallel with processing the previous one.
So, ma'am, the overlay in this case is the floating point computation unit?
No, the overlay is this block, the FFE block, that does this computation of the features based on these extracted features. So these are simple features. You use that, they run some complex floating point computations on these features to get what they call meta features, which are basically aggregation of these more basic features. Okay. So this is the overlay. You can see here that it has been instantiated multiple times, right? 8 times on the single FPGA in this diagram. And then this will come with its own instruction set and some kind of compiler which will take, this operation coming from software and translate it into computations that can be done with the ISA of this overlay. And that is what they talk about here. Okay. Okay.
So is this still in use, admin?
Actually, they have, I think they have more sophisticated versions of this in use now.
Oh.
But it is being commercially used. So when you use Bing search, right, actually you are running it on an FPGA. It's the same thing with Google. Google, of course, has a TPU now. But some pieces of Google search are actually accelerated on FPGAs.
So actually, a couple of years back, when I and Lavanya tried to do a hackathon for FPGAs, we got some accounts in Catapult cluster and we tried a bit.
Oh, okay. Okay.
It's a good experience. Yeah, I think at that time the challenges there again. So we are doing the designs in BlueSpec and we have to tie that design to the shell of the Catapult. That's where we struggled a bit, and
right.
we had to do a bit of hacking there.
Right.
But we didn't continue that. I think one idea we thought at that time is, the advantage with Catapult cluster is the same things. If the design doesn't fit into one FPGA, we can use multiple FPGAs and do all sorts of interesting stuff. And,
right.
Lavanya, finally, did we get to run any design on the Catapult cluster, or we couldn't?
I think we could. The one that Ziawul was working on, I think we could successfully run. Also, we could run, Sahiti was running on something, right? During the hackathon, she had picked up a project. I think that was also successfully run on the, yeah.
Okay. Nice.
So, tools like IIITH actually are now gaining traction precisely for this reason, because handling that interface, if you have to custom design hardware, becomes tricky. And so, all these frameworks try to take care of it as much as possible for the user. So it becomes more plug and play. But most of these commercial things, they're all kind of in the process of development. It's all a very new area of both industry work and research.
So if you think of the F1 instances, so F1 instances have 4 FPGAs, right?
4 or 8, I'm not sure.
Yeah, 8 FPGAs. And are they connected by some network? Like, is it possible for us to distribute a design across all the 8 FPGAs? And also, that is one question. Second question is, how much support IIITH has in multi-FPGA synthesis? And
yeah, so for multi-FPGA, we are building some of it. So we do have tools, if you had something and you had an application which you could describe as a graph, right? And then you map each graph to different FPGAs. And then we'll have a resource manager that takes care of that scheduling and all. So that is in development. I'm not sure how many features are available today to users, but if there is interest in finding out about that, I can find out and then maybe, spend 15-20 minutes in one of the lectures talking about what's available there. Multi-FPGA, what is available in AWS Educate, again, I'm not sure. So that maybe we should take that question to Parimal and then get back.
Yeah, I think in Educate it is not there. You can use only one FPGA in Educate. I'm just talking generally from a research problems perspective to
No, in general, actually, the goal of IIITH is to support a multi-FPGA environment. And that is also the goal of things like AWS, right? As they have said in this paper, the ability to combine multiple FPGAs gives you the benefit of scale. You can pick the scale that works for you. And I think all these companies figure out somehow based on workloads that this 8 high-end FPGA seems to be the right scale on a single card.
Yes.
These guys also have used 8. So yeah, so it is it's interesting. So I can find out and then come back.
Sure. Yeah.
Ma'am, can you once go to the 8 FPGA design?
This one?
Yeah. In that only FFE0 and FFE1 has overlay, or all of them have overlay?
No, so the FFE0 and FFE1 is the overlay for doing the fast feature extraction.
Free-form
Expression evaluation. Free-form evaluation.
Okay.
What is the inter-FPGA bandwidth? I missed it, maybe.
They've had it somewhere in this paper. Yeah. So basically, 20 gigabits per second peak bidirectional bandwidth.
Okay.
So it is pretty fast, and that is what makes it feasible to do it like that.
Okay.
But then this, right, to go back to the question earlier, so the minute you add this kind of network, you also add to your power cost. And you need additional networking provision, as I think Aditya or someone else pointed out.
Yeah.
So in all these, right, some of these things you don't, some certain factors, right, like the form factor of the card, cooling, they all become very, very critical factors in commercial deployment in a data center just because of the cost involved, right? An interesting thing to keep in mind, when you work in a lab on an FPGA which is connected to your laptop, these are not factors that you typically think about, right? Yeah. So in the interest of time, I won't, necessarily go through all the, plots in detail showing the performance improvement. You can actually go through the paper and read it. I'll send the paper over. And here, right, so you can see, they've plotted, it's a very comprehensive study. They've looked at when you inject one document at a time, you inject multiple requests at a time. How does the latency vary with throughput? And they show that, you are able to increase your aggregate throughput and at the same time reduce the tail latency as you keep increasing the average rate. So they have some numbers here. And the other interesting thing they show is that you actually can do it at running at a fairly, this is not a very high clock frequency, right? If you think about it, 150, 180 megahertz is the highest clock frequency that they are showing on their FPGAs. And the usage also is reasonable. Okay. So you're able to get this with lower throughput and area. And so they're saying, yeah, in the long term, they could actually look at, maybe fitting more logic or clocking this at a higher speed and getting even more performance improvement. So
one quick question, Patni. So why is that they say that usually when they use these tools, like I see they are able to easily run at 200 meg or 250 meg easily. So is there any reason why the clock frequency, they are not able to hit 200? Is there any complexity in any design which is preventing this?
So in this, if you see, right,
Or is this because it's a very old work and
this is probably
could
one
be-
reason is old work, and they themselves say, right, there is substantial headroom to improve. So this must be a preliminary implementation is my guess.
okay.
But the minute you start hitting, we definitely see this, the minute you start hitting logic utilizations of 70 to 80%, timing closure becomes more challenging because you need space to route everything.
Mhm.
And you can see that those are the blocks actually which tend to run at lower frequencies, right? You see.
Hmm. So is it the same even for DSPs also? Like if you use 100% DSP, will it be hard to get timing closure?
Yeah, depending on whether the data path going through the DSP is critical or not, it could be.
It could be.
So we definitely see challenges there. So when you get the RAM and DSP utilization to be very high, especially RAM, because RAM, when you use it heavily, almost always tends to be on the critical path, especially for these types of applications. You're bringing data in and out.
Mhm.
So there, those tend to be difficult.
But, recently we saw one paper and they are almost showing 100% utilization, and we were wondering, like whether timing closure problems wouldn't have occurred to them or
Maybe. I think there are, also people sometimes they, handcraft some of these designs to squeeze performance out of it. You can, if you know your architecture very well.
Okay.
We know of customers who, for example, may hand place, DSPs or memory to improve your performance. Or, hand constraints. So there are a lot of tricks for squeezing performance. It does get harder as your utilization increases beyond a point. Typically 70-80% is that point.
Okay.
So so now let us go back and look at some of the other hardware considerations that they looked at, right? So we talked about this broad design, right? So they have used PCIe, and this is very typical in most accelerators because that's the standard way to communicate to an FPGA, to a CPU, to a server. Today you would have learned about we talked about this in one of the earlier lectures, right? There are now these new protocols called CXL and C6, which are basically meant to allow coherent communication between accelerators. But all that is after this paper. So that is one reason why they have used PCIe. And they have added local DRAM. Cost looks like it was a consideration here, and they have sized it based on whatever data they needed and their power and cost thing. Okay. And then here, so you can see what's very interesting, right? When you read the paper, and I'm hoping all of you will at least get an appreciation of this. You look at all the kind of factors that they have to take into account. Right from what connector they use at the back of the server. You see this, they use the mezzanine connector so that the heat from the FPGA did not disrupt existing system components. And then you notice the CPU, the FPGA, because it's attached to a host, it is subject to higher temperature because the air around the server is hot, right? So they actually used an industrial grade FPGA which is rated for higher temperature operation, right? Then they had to add some EMI shielding. These are, I think, typical data center design considerations. And it is interesting to go through this paper to get a view of what some of those design considerations are. So they've had to add EMI. EMI is electromagnetic interference, shielding to the board. And you typically get EMI when you have very high speed, signaling happening, because those waves will interfere with each other. Right?
We call it, it is like spectrum, I would say, spread spectrum or something we call it.
Yeah, I'm not an expert on that. So,
okay.
yeah, I think if you can read up, if you have a specific question, I can read up or try to get the answer for you. And yeah, right. And then they have, they have this power requirement, right, of 20 watt per board. And this has met both their thermal requirements and their power requirements. Right? Then, how they have actually organized the servers so that, they know how many pods they have, how do you arrange it so that, it fits in the tray, which fits in the server rack. Those are interesting, and then the choice of the network topology is to balance both, the ability to communicate between two servers and also the complexity of the cable, which depends on the backplane that they use, how many ports they have, what is available there. Right? And then, you can even look at, some of the other factors that they have talked about, right? You can actually service a server by pulling it out without unplugging anything. So this makes maintenance simple. Okay? So these are all some, interesting things that you would not normally think about if you don't work in a data center. So the other interesting aspect that this paper talks about, and that is in section 3, it's not hard to read. So I would encourage all of you to go and read it in more detail. I'm just sort of going through some of the main points. Is this whole, support for resilience. Right? So if you see here, right, they talk about, so if there is a bit error, right, it can, it can cause very high level disruptions in your data because many of them add up. Right? And remember what they're accelerating is search. Right? So it is very, very data dependent. Errors can be very expensive. So they employ double bit error correction and single bit error correction on both the memory and the inter-FPGA communication. Right? And of course, that results in a reduction in bandwidth, but it is worth it. Right? Then you see, they have a lot of redundancy in terms of error correction. So they have ECC on the SL3 links, which go between the FPGAs that correct single and double bit errors. And then in addition, they have a CRC check at the end of packet transmission, which can correct anything with 3 or more errors, at least detect, not correct. Right? And then every time they detect a double bit error or a CRC failure, the packet is dropped. And they have a software protocol for dealing with that, right? And then they have, they actually, run these for. They have an SEU scrubber, which takes care of single event updates. So single event upsets. So here, single event upsets get costly if they disrupt the configuration of the FPGA. That is, you expect that it's programmed to do a certain function. And remember, FPGAs are programmed by writing to memory. Now, if a bit gets flipped, suddenly, lookup table on the FPGA may be performing a different function. So it has to be constantly scrubbed, And so that is what this SEU unit on the FPGA is for. It goes in and keeps scrubbing the configuration of the FPGA and make sure that it is correct. Right? So this ensures that your soft errors don't become very expensive. And again, right, all these become more of an issue in the data center because of the higher temperatures at which FPGAs run, because of the high-speed wires which are there. All those make these prone to FPGAs, right? Prone to errors and upsets. Right? Then, what are the different types of operating problems that you can have? For example, if an FPGA is being reconfigured, the host actually sees it as a failed device. Right? And so how does the host deal with it? Right? So their software stack has to take care of the fact that it needs to understand which FPGA is being reconfigured, which FPGA is actually failing. Right? Does the FPGA, corrupt its neighbors by sending some random traffic? Right? So all this is done through, having clean signaling between the FPGAs, right? And then, ensuring that you handle this whole reconfiguration in a very clean way by doing this transmit halt and receive halt. Right? And then they have this high-level mapping manager software, if you remember. So that takes care of managing which FPGAs are being configured or reconfigured, and setting the interrupts and so on accordingly. And then the section 3.5 talks about this notion of a health monitor, which manages any errors. So it contains a vector and it has flags for different types of errors. So you can detect it and give this failed list to the mapping manager, so it knows whether an FPGA is up or an FPGA is down. Right? And then you can actually go in and maintain if you need to. Right? And then this is another interesting thing. They have what they call a flight data recorder, which keeps track of some data for the FPGA, and it keeps this in memory. So you can actually, they do it for a very limited time window, but it allows them to, diagnose and resolve some of these odd problems. It gives you an additional layer of debug. So so these are some of the interesting aspects about designing a commercial system, which I hope will be basically of interest to all of you. What you're looking at in your projects is at a very different scale, but it is still nice to understand that these are parameters that commercial deployments have to take into account. So that was why I selected the paper. So I hope you all enjoyed the discussion. I will send the paper out maybe.
Sure, Padmini. I think we will make this paper a mandatory requirement. There are lots of fun things in this paper to learn.
Yeah.
So, yeah.
How did you all find the class? Any feedback? I mean, was doing it this way rather than through slides, was it understandable to everyone? Was good. Okay. Anyone who felt the pace was too fast, please raise your hand. Okay, too slow? Okay, cool. Thank you. So,
Okay, thanks a lot, Padmini. Thank you, everyone. So we will meet again on Wednesday. Wednesday, we will revisit systolic arrays topic again. And the next Saturday is your exam. So this paper you should read carefully. This will be included as a part of exam reading assignment. So continue to work on your projects, keep meeting your mentors and make steady progress. So yeah, so that's all for today. So thank you everyone.
thanks.